Hi everyone, this is Manoj Gopale and this is my presentation for our final project for the course ECE 505 Model Integrated Computing at University of Arizona, Fall 2016, taken by Professor Dr. Sprinkle. In this presentation, I will give you a brief background on the need for such a tool and then take you through a live example of using this tool. So this tool is basically used for hardware designing. So why is hardware design required? Hardware is present in many of the day-to-day components that we use, ranging from our cell phones, radios, computers, supercomputers. So where do we start learning about the hardware? To learn about hardware, one has to basically go to the basics. Each hardware is composed of logic gates like AND, NAND, OR, etc. So learning how these works gives you a basic understanding of how an hardware will work using these components. So what are the tools that a user has to use before he can implement the design? So suppose we are the user who has an idea. So this is converted to a machine readable code using a hardware description languages known as Verilog and VHDL. This is also used to create something known as test bench that is used to test your design against various inputs. This is compiled using compilers which are available for free. These compilers create a waveform like interface that can be used to verify the results after the simulation have been done. So it basically involves, so a user basically is dependent on knowing VHDL or Verilog to check his design. So where does Verilog suite help a user? So Verilog suite comes in between the user's idea and using the compiler. It removes the dependency of a user to know Verilog or VHDL to convert his idea from a graphical representation and check its result. So let's say we have a circuit that is a full adder that is shown on the left. So when it is taken through the Verilog suite, it will convert this diagram into a Verilog code and a corresponding test bench that is required to test its results. This is one of the simulation that I ran using a compiler known as Vivado by Xilinx, and it shows that our design is working fine with these results. Now coming to the tool itself, the tool this is my composition meta model of the Verilog tool. So it consists of two subclasses, Verilog suite lang and Verilog test bench lang. So Verilog suite lang is used to create and design the circuits and create your Verilog, and test bench is used to create the corresponding test benches that can be used to test your language. So let's say we have to create a new Verilog circuit. You create a Verilog drawing child, and you can rename it as, let's say, a full adder. So now we have a full adder. We can drag and drop components from the left hand side inside your drawing sheet like this. This is the gate, these are inputs. Let's say we want another XOR, and an output that will store the results. Maybe you have two outputs, maybe you have another input. Connecting these is fairly simple. You can just drag from the inputs and connect them to the input ports like this. and an output like this. So let's take a previously created example. This is a full adder that was shown in the slides earlier. So how do we, there is so when we go to the plugin, we have a Verilog, create Verilog and Verilog check test. So Verilog connection check will test if the output net name coming out from a particular gate has the same name or not, and if you have and you don't have any net that are dangling in the design. So let's say we create a net that goes from this XOR to this AND, and we don't name it. So let's do a connection check. So we see that it shows we have an error, and it will clearly mention which two nets are violating. So in this case, net with path this from XOR is not labeled, so it is saying that this net is not labeled. So let's label it as H1. As we can see, it also has a previous net which has the name X1. So these two nets are coming from the same output of this XOR but have two different names. Even this is a violation for our circuit, as we can't have two names. Names usually denote the output coming from a particular gate. So if you have two different names, you'll have, it means that it is coming from two different gates, which is not the case in here. So if you do a Verilog con check again, you'll see results. It will again show an error, and it will say that nets from source XOR with path do not have a matching name as we expected. So let's say we name it as X1. Now this X1 is matching this X1. Let's do a connection check again. Save and run. Show results. Operator has more than two connections. Clear results. So one of the key requirement is that an operator cannot have more than two inputs. Like this AND gate cannot have more than two inputs to it. So let's delete this. Now our circuit looks fine. Verilog con check, we should not show any error. Voila, no violations are seen. Now to actually create Verilog, you'll have to click on create Verilog, save and run. So it will create the Verilog corresponding to this. Download. So if we open this file, we see that it has created a Verilog code with the name full adder to it that we gave, and inputs as A, B, C, outputs C out and S out. So this is how a basic circuit can be checked, and a Verilog can be generated for it. Now to create a test bench, we again go to the root, we create child, and we do a test bench drawing. Test bench drawing, we open this, we see that we only have two models that we can drag and drop. One is the module name and one is the state. So let's say test is the name. So a module name is actually the name of the module and what the inputs and outputs are for this module. So if you click on this, you can see on the right hand side in the attributes tab, we have attributes that we can set. You can set multiple inputs. you can give a module name, let's say full adder. So now your module is full adder, and you have outputs that you can define for this module. And states are actually the input values against which you have to test your design. So how do we set these values? So let's say we have this state, we double click on it, you go inside the state model again. Clicking on this, you can give the names. So let's say your first input is A, and the value against which you want to check is 1. Let's say you have B, you want to test it against 0. So this is how you have to actually define the values. So this is for one state. You can do this for multiple states. State is actually a time frame in which you can check, in which your input values are stable for that particular amount of time. So if you have to test for let's say A is 1 and B is 0, you can test it at this state. Next, you want to test your circuit with A0 and B1. So you give value of A as 0 and B as 1 here. Next, suppose you want to test for A equal to 1, B equal to 1. So this is how you create the states, and then you have to join this module to the states in this way. So this will actually create a sequence of events from state 1 to state 2 to state 3. So I have a full adder test bench that I had already created. It has inputs as A, B and C. So in this state I am actually checking at A equal to 1, B equal to 0, C equal to 1. So I have multiple states. I have full adder, which has inputs as we can see AF, BF, CF, clock, register, clock reset, and outputs are S out and C out. Here also we have a connection check, like we can't have more than one connection that from any of the module to the states. So if you go and check for test bench check, this will give you an error saying that more than 2 input connections are there. So state with path m/2 has more than 1 input connections. So as we can see, state with path m cross 2, as we can see, has more than 2 input connections. So this is a test that you should run before creating any test bench. So if we save, voila, there are no violations now in our circuit. And if you do create test bench, it will create test bench for the module full adder for all the given states. Oh sorry, show results, test bench.v. We see that a test bench has been created with a full adder, and it has instantiation of all the inputs that are there: A, B and C, clock reset, S in, S out and C out. And these are the values of state 1, this is of state 2, these are of state 3, and this is of state 4, and then you finish the design. So these two files, verilog.v, the Verilog file that was generated after using the tool, and the test bench is used as an input in Xilinx Vivado tool to create the waveform that you saw in the slides earlier. So this is one of the basic examples. If let's say you have a circuit design which is as complicated as shown in circuit 1. So in here also the basic idea is that your design should not have should not be should not have any violations in terms of the net names, and there should not be any wire that is dangling. So that's how that is what you'll get when you do a Verilog connection check. So so this looks like a complicated design to actually write a Verilog code for. So let's say we create a Verilog code for this. Save and run. Show results. When you open this, you'll be able to actually see two files. So I'll come to the latency file a bit later. So the Verilog code will look like this. So it has all the components, and it actually takes in the inputs and the outputs on the first line. It creates this data set which is used to actually write the main code of the design. Latency file is actually the distance of an operator from the sinks. So this is actually useful in scheduling algorithms where you want to know the distance of an operator from the sink, so that you can use it in ALAP and ASAP scheduling that is further used in algorithms such as force directed scheduling or use algorithm. Those are used for resource minimization and with a latency constraints. Coming to the full utility of the test benches, let's say you have created two more circuits. This is circuit 2, this is circuit 3, and you want to test all these at the same time, rather than writing test benches individually and then checking them. So this tool helps you in writing a single file that you can use as a test bench for all the three modules. So here I've created a module with circuit 3, circuit 2, and circuit 1. I have different states in which you have set input values for which you have to test your circuits. Again, if you create test bench, save and run, show results. So you see that this is a pretty huge file that is created, and so this is basically a very redundant work that one has to do. Writing a test bench is like you'll have to instantiate these input values one by one, and then do it for each circuit one at a time. So instead of that, you can use a graphical interface that the tool provides to input your values, and you can change these input values by going in and simply changing this. Suppose you have b equal to 8, you can change it to b equal to 10, and then test the design for that without actually going through the entire process of creating a Verilog code again. So this is what the Verilog suite will be used for. Thank you for listening. Have a nice day.